So thank you for coming back to the second. I don't like this. So I'll make it very brief. So we're very happy to have Maryna Viazovska for the second Simon's lectures. And between yesterday and today, she was elected to the National Academy of Sciences as a foreign member. So congratulations, Maryna. And please take the floor.
So thank you, Michael, for the introduction. So today I will speak about packing spheres in very big dimensions, and I will focus on the constructions of good sphere packings. So in the last lecture yesterday, we have discussed sphere packings, and we have discussed upper bounds for the sphere packing problem. And so for the upper bounds, we need to find some argument why the sphere packings cannot be too dense. And usually this is a somehow complicated game to play. On the other hand, for the lower bounds, what we have to do, we have to present some sphere packing or to prove that it exists and still has a big density. And so, of course, this way in small dimensions, we can just do brutal search, find good examples numerically, or search among all the possible ideas and constructions we can have, and some of those ideas will be good, and they will give us good examples. So, for example, here is a good constructions in dimensions 1 and 2, and so here for lower bound, we just compute the density of these packings, and we know what it is. And so in a finite dimension, so these are all the dimensions in which we know the value of the sphere packing constant exactly. So I will remind that the sphere packing constant in dimension D, this is the maximal possible density of a sphere packing in d-dimensional Euclidean space. And so only in these 5 dimensions we really know what is the maximal possible density and which are the best configurations. And so here we know it in dimensions 1, 2, 3, 8, and 24. And so then one of my favorite questions in this area is what happens when dimension becomes very big when it goes to infinity. And so we do know that the density of a sphere packing decays exponentially as d goes to infinity. And then the question would be at which rate, and we of course can ask this question by both producing better upper bounds, but also by producing better examples or proving the existence of better examples. And so maybe an easy lower bound on the density of the dimensional packing is the following statement. So a saturated packing in dimension D always has density at least 2 to the minus D. And the best known upper bound at the moment, it's an upper bound which is derived by the linear programming method, which I have explained yesterday. So Kabatansky and Levenstein, they were able to construct this family of I would say maybe they're not magic functions according to my definition, but somehow the most magic functions for big D. And so so they showed that the sphere packing constant has to decay at least at this rate. And so here you can see that there is somehow an exponential gap between the lower bound and the upper bound. And so the people who try to prove upper bounds, they usually come up with different philosophical arguments why Kabatansky-Levenstein bound should be morally the correct one, because it's very, very difficult to beat it. And then people who try to improve on the lower bound, they also say that at least probably the main somehow term should be 2 to the minus d, and then we can have some incremental improvement, because it's very difficult to get any better improvement. And so I don't really know where the truth is, but today I will show you what kind of improvements can be made on the lower bound. So how can we improve this simple 2 to the minus d? And so first let me show you, okay, so I could not resist and show you how the proof of this statement works. So how do we prove that the saturated packing in d-dimensional space always has density at least 2 to the minus d? And so what does it mean for a packing to be saturated? It means that we choose our non-intersecting balls, and they're chosen so that we cannot add any more, one more ball to this configuration. If we add one more ball with any center, it will necessarily intersect with one of the existing spheres. And so how can we, if we know that the packing is saturated, how can we visualize it? We can, for example, take our balls in the packing, and now what we do, we inflame our balls twice. So consider balls with the same centers, but the radius twice bigger. And then if this is indeed a saturated packing, then what would happen is that these new bigger balls, they have to cover all our space. Because if there is a hole somewhere for, like in that picture, so there is one hole which is not covered by this inflated blue balls, and so there we can put one more center and one more ball, and it will not intersect any other balls. And so now the final step is to compare the volume of balls of radius r and the balls of radius 2 to the r, and in dimension d, the volume will differ by this factor 2 to the minus d. So this is where the 2 to the minus d is coming from. And so now what I would like to speak about today is about how to improve on this 2 to the minus d. And so here before I do so, I would like to introduce lattice packings. So it seems like studying all the packings is difficult, but maybe if we insist that our packings have extra structure, maybe this will make our life a bit simpler. And so the natural symmetry that we might have in Euclidean space is a symmetry of the underlying abelian group. So d-dimensional lattice, it's a discrete abelian subgroup of full rank. And so here's an example of a two-dimensional lattice. Then for each lattice, it will have, among all its vectors, it will have its shortest non-zero vector. And then if we can, to each lattice, we can assign such a lattice packing, which would consist of balls with centers at the points of our lattice, and radius equal to the length of the shortest non-zero vector divided by 2. And so this way, the density of this lattice packing will be equal to the ball of radius r minimal divided by 2, divided by the co-volume of the lattice. And so this way, we can rephrase our problem now, so that, for example, we consider only lattices of covolume 1, and among those lattices of covolume 1, we want to choose lattices with the longest, shortest vector. And yeah, so just for convenience, we already know that this factor 2 to the minus d, it's somehow, this is the constant we trivially have, so for a lattice, I will denote by delta d lattice. It would be the lattice packing constant. So packing constant where only the lattice packings are competing. And so just to simplify my notation a little bit, because in all my estimates, so the 2 to the minus d will not go away. It will be about the sub-exponential factors. So I will introduce this constant cd, which is 2 to the minus d times the lattice packing constant. And so for the lattice packing problem, so here it can be solved in a bigger number of dimensions than the general sphere packing constant. So here it has been solved in all dimensions up to 8 and also in dimension 24. And in dimensions up to 8, it's actually a very old result. So I think it goes back to the beginning of 20th century. And the dimension 24, it was solved by Henry Kohn and Abhinav Kumar. So they have proven that the Leech lattice is optimal among lattices. Before we have proven that it is optimal among all configurations. And also, it seems like what is interesting about this list of numbers, it seems that dimension 9 is a computationally very hard problem. So I spoke to people who work on this from the computational side, and they consider it to being a very, very difficult computational problem. That's because the configuration space of lattices, of course, it's finite dimensional, but by the dimension 9, it gets so big that it becomes difficult to somehow make any kind of exhaustive search, or of course also to giving an argument why the search actually gives the right result. And so today I would like to speak about also again like lower bounds for this lattice packing constant, or its normalized version. And so, okay, so here is the history of improvements on the lattice packing constant, and a very old result which goes back to Minkowski tells us that so the lattice packing constant is also, so the constant CD is bigger or equal than 1, which means that the lattice packing constant is also always bigger or equal than 2 to the minus d, or even 2 times 2 to the minus d. So I did not include 2 here, but it's maybe not so important. So yeah, so at least for this somehow lattices, they can beat this saturated bound. Then this, for a long time, there have been various improvements on this result, and at the more or less middle of 20th century, Rogers have gained this linear improvement on the constant. So he showed that CD is bigger or equal than some constant times d, the dimension. And then there have been several improvements not on the rate of the growth, but on the constant in front. Then in 2013, Venkatesh was able to get another improvement, which is asymptotically better than linear. So somehow he used the idea introduced by Stephanie Vance, but then enhanced it. And so he have proven that maybe not in all dimensions, but in a certain sequence of dimensions, we can have such a like d time, so like this log d improvement. And so, but this was, but now it seems like we live at a somehow special time when everything becomes faster, and even the lower bounds on sphere packings are being updated more regularly. And so 2 years ago, there was a new exciting result by a group of combinatorists who were able to prove this bound not for lattice packings, but for generic packings. So here they prove that there exists lattice packing with density at least like 1/2 times d times log d. And also their method, it works for, so it doesn't guarantee that this packing which exists, it doesn't have to be a lattice packing. So it might not have a good structure. And so of course also there many people would then think that, okay, probably log d, this is the correct bound, because how can it be otherwise? But then actually this month, the new result came out. And so this is a theorem of Boaz Klartak, and he have proven that we have that there exist lattices such that the corresponding lattice packing has density at least a constant times n squared times 2 to the minus n. Okay, yes, n is d. I'm sorry. And yeah, so my plan for today is actually to go through these three ideas: the idea of Venkatesh, the idea of Campos, Janssen, Michelin, and Sarasbude, and somehow briefly over the idea of Boas-Clartak, even though I should confess that I do not somehow understand all of the parts of his paper yet, but the idea seems to be very exciting and interesting. And so let me start with the probabilistic method, which helped to prove the Minkowski theorem. And so here, maybe one thing I should say that essentially all these proofs, they rely on randomness. So here in the heart of all these ideas is the randomness. So we are choosing a random lattice, or the lattice that comes out of some random process, and then we prove that with a bit probability this lattice will have, with a positive probability, this lattice will have long shortest vector. And so let's consider the space of random lattices. And so the space of random lattices, it's a very nice space with a very nice underlying algebraic and geometric structure. So let's look at the set of all d-dimensional, all lattices in Euclidean d-dimensional space, such that their co-volume is 1. Then, of course, if we want to describe such a lattice, the easiest way to do so is by giving a basis of the lattice. And in this sense, we have this correspondence between lattices and d by d matrices of determinant 1. But then, of course, here if we have a lattice, then its z basis is not well defined. There are many possible z bases, and so the choice of z basis is controlled by the group SLDZ. So it's a group of d by d matrices with integer coefficients and determinant 1. And this way, the space of random lattices, it naturally can be considered as this quotient of the group SLDR by the group SLDZ. And so the group SLDR is a locally compact group, and SLDZ is a discrete subgroup inside that group. And so we can consider a Haar measure on the space of matrices SLDR. And so here, what is an important fact is that the quotient of SLDR by SLDZ, it will have finite Haar measure. And so we can renormalize it so that the volume of the quotient will be 1. And then we can think of it as a probabilistic measure. And so somehow now, of course, what one could try to do is to look at this random lattice and to, for example, compute the average value of its shortest vector. But unfortunately, this is not a very nice behaved function. It might be difficult to do it directly like this. On the other hand, there is a class of functions for which we can easily compute their expected value on this set of random lattices, of the space of random lattices. And these are so-called lattice sum functions. So how does it work? It works in the following way. So let's choose a function f, which would be a bounded function with compact support in our Euclidean, invariant Euclidean space. And so then for each lattice lambda, we will consider the sum of the values of f at the all non-zero points of lambda. And so here an important result by Ziegel tells us is that if we look at this lattice sum function as a random variable on the space of random lattices, then its expected value will be equal to the integral of the function f over the Euclidean space. And somehow, intuitively, this is not a very surprising result. It kind of makes sense. For example, if we want to compute the integral of f, one thing we could do is compute the values of f in some lattice and just then sum it up. And so our lattices have covolume 1, so these sums, they would be something like Riemann sums. But here now, because we are looking not only, of course, for each given lattice, there will be some error. But then if we are averaging over all possible lattices, then all the errors will cancel out, and we will just have the integral. And so now if we have this with the Ziegel's theorem, we can actually prove Minkowski's theorem. And so, okay, so this problem here I wrote down more people who kind of reproved this theorem or gave different proofs of it at different times. And also the proof I'm giving now, it's not the proof that Minkowski, for example, had in mind. He had a different method in mind. And yeah, and so the method which so here what I suggest is to for us to take a ball with center at 0 and consider the indicator function of f and the lattice sum associated to this indicator function. And then, of course, so in this way we will if we compute the average value of this function, we will know how much on average each lattice has inside of our ball. And if this average is small, then we would know that maybe there is one lattice which has no points, no non-zero points inside of B at all. And so here we will choose our ball so that it has volume 2 minus epsilon, where epsilon is a small positive number. And then the average value, the expected value of the lattice sum function associated to the indicator function will be equal to the volume of the ball. And so it means that we will have a lattice such that it has so its intersection of its non-zero vectors with the ball has less than 2 points. But then if the intersection has less than 2 points, then it has 0 points. This is because each vector, if a vector is contained inside of the ball, then its negative is also contained inside of the ball. And so this way we will see that there exists a lattice such that its intersection with the ball is 0, and therefore we will have the corresponding lattice packing of density at least 2 to the minus d times 2 minus epsilon. And so now the idea of the Venkatesh is actually to consider not all of the lattices, but only a subset of lattices with special symmetries. And so what he suggests, so Stephanie Vance, she considered lattices with symmetries given by the quaternion algebra. And Venkatesh, he suggested to consider lattices with the symmetries of the nth cyclotomic field. And so let me tell you a little bit how to construct such a lattices. Okay, so we take a cyclotomic field, which would be Q adjoint a primitive nth root of unity. And so then, of course, the group of nth root of unity group of the nth roots of unity will be acting on the field K just by multiplication. And so now what we would like to construct a lattice embedded into an Euclidean space. And the classical way of doing it is by considering Minkowski embedding. So we take our number field, and our number field So cyclotomic field, it's a totally complex field, and so it will have d over 2 complex, different complex embeddings into complex numbers. And so now what the Minkowski embedding of the field works in the following way. We take an element of the field, and now we consider all of its embeddings, and this gives us a vector of length d minus 2 in the complex space C to the power d over 2. And so to turn it into a Euclidean space, we also have to consider the scalar product. And the scalar product here, it would be the trace norm. And yeah, so the degree d here of the field in this case, it will be equal to the Euler's totient function of n. And what Venkatesh suggests for us to consider 2 copies of the field. And then if we embed our ring of integers into, consider their Minkowski embedding, this will give us a lattice in this Euclidean space, and we are taking 2 copies of this lattice. And so then what we can do, we can consider, we will consider the action of this group, of the group SL2 of the KR on our 2 copies of the Minkowski space. And so the action of this group, it will preserve the symmetries. And so what will happen is that each lattice inside of this space, it will be invariant under the action of the group of nth roots of unity. And so what is also important is that the action of this of the group of roots of unity, this will be orthogonal action with respect to our chosen scalar product. So we will have this group which does not change our scalar product, doesn't change length of the vectors, and also preserves all of our lattices. And so, so now what is interesting here, so now if we take any ball with center at 0, and we consider the intersection of our, okay, so maybe there is a typo here. Okay. So we consider a number of elements of our non-zero vectors inside of the ball, then we will, okay, so that equality has to be changed by the inclusion sign. So we will, all vectors now, they will come in these packages of n vectors. And this is because if we take one vector, we'll let the group of finite units acting on it, and it will produce for us n vectors. So the orbit will always consist of n vectors as this group mu n, it acts, it doesn't have fixed points in our Euclidean space, except for the 0. And so we will know that the function, which is this function which counts the number of points, it will always have, its values will be always some integers divisible by n. So now we can apply the same, and so what is an important also fact here is that the Siegel mean value theorem, it also works in these settings. So there is a version of Siegel mean value theorem which is also correct for this probability space. And this actually somehow, okay, so here this is probably an observation by Venkatesh, but essentially this is the Ziegel-Weil, partial case of the Ziegel-Weil formula. And so, yeah, so this a similar formula will be true again for all compactly supported bounded measurable functions, and in particular it will be true for the indicator function of the ball. And so now we can apply the same method which we used to prove Minkowski bound. So here we are considering also a ball, and this time we choose a ball of the volume n minus epsilon, where epsilon is a small positive number. And then from the mean value theorem, we will know that there exists a lattice which contains such that the number of non-zero lattice points inside of the ball is smaller, strictly smaller than n, and if it is strictly smaller than n, then it has to be 0. And so, therefore, we know that it is a good sphere packing which is good enough. And so corollary would be that the lattice packing constant is bigger or equal than this d times log d for a sequence of infinitely many dimensions.
Sorry, Maryna, just to clarify, so what are YD indexed by? The lattices are...
Okay, so YD they actually, okay, maybe YD actually depends on a number field K.
Yes,
so,
like how do you generate, okay, so like you define the collection of lattices, right, and they're sum of lattices different from...
Okay, so this is, okay, so this is this...
okay, so it's indexed by elements of SL2K, okay.
Yeah, and in fact, maybe I can write down more explicitly what these lattices have to be. Okay, so maybe I can clarify. So, okay, so maybe so this group here, in fact, it would be the same as so it would be a product of d over 2 copies of SL2 over C. And then this the group SL2 OK, it will be a discrete group inside of this group. But then somehow I did not include too many details in the slides today because I plan to speak more about this construction tomorrow. And then maybe also one important remark that of course this space YD it will live inside of, so it lives inside of the space XD, which was a space of all lattices. So it seems that using symmetries in this way, it gives us this d times log d improvement over the saturated bound. So what are the other ideas on the table? And so actually together with my PhD student Nihar Gargawa, we tried also other symmetries. So the symmetries of the cyclotomic field, they are not the only type of symmetries we can use. So this was Nihar's thesis was to construct other spaces of lattices with symmetries. And so Nihar constructed spaces of lattices with symmetries by a finite dimensional division algebra over Q. And yeah, so this is a kind of result he was able to prove. So if we have a finite dimensional division algebra over Q, and we have an order of this division algebra and a finite group, which is embedded into a multiplicative group of this order, then he could prove such a bound for the lattice packing, such a lower bound for the lattice packing constant. But then actually so there is a classification of finite groups which can be constructed in such a way. So they're called Amitur groups. And so we went through the list, and it turns out that actually cyclic groups are the best among them. So the kind of groups we could get here, they were still very close to being cyclic groups, maybe with some small improvement, like small extensions of those. And so this was the best bound Nihar was able to prove. So it's slightly worse than log d. So it's log d to this power, which is smaller than 1. But then maybe like one interesting phenomena we observed that actually for small d, this thing was still kind of better. But for a while, this was better than cyclotomic groups. And so now what's about other ideas? And so as I told you, like two years ago, this new paper has appeared, and the new paper tells us that we can actually, there exist fair packings of density at least 2 to the d times d log d. And so here the idea comes from the graph theory. So here, in the contrast to what I showed to you before, how we can use symmetries to improve packing results, here the construction seems to be random, and so it's somehow maybe a better exploration of randomness. Because, for example, in the proof of the Minkowski theorem, we are just computing the average and we are done. But here the idea is to really dive into the like to introduce kind of like a random process when our packing at the end would be a result of this process. And so here is how the let me set up the scene to explain some key ideas of the paper. So first, how to connect a sphere packing problem to a problem in a graph theory. And so here there is actually a quite standard way of doing this. It is by considering what is called the contact graph. And so let X be a discrete set of points. Then for this discrete set of points, we can assign a graph where the vertices of this graph will be the points themselves. And we introduce edges between two different points if their distance is smaller or equal than 2r. And so then if we look at this graph, then the packing problem becomes essentially an independent set problem inside of the contact graph. And so here is an example of a set X and a contact graph associated to this set X and radius R. And so, so if we take, for example, a random set of points or set of points which comes from a Poisson point process and consider the associated contact graph, what can we say about this graph? So it turns out that we can actually control certain things about this graph. So maybe one small remark is that usually, normally in graph theory, what we do, we consider like finite graphs. That's a nicer theory from that. And here the graph would be infinite. But then there are, of course, remedies for this, either to consider periodic sets or just to say that we are working just in a very big box. And in fact, we have like a very big but a finite number of points. And so if we have our contact graph, so what kind of are the quantities? So this like independent number is or the size of the largest independent set is what we would like to find. But then what do we know about this graph and what can we control? And it turns out that we do have quite a good control over the average degree in this graph if we take it on random. And we even have a control over maximum degree of the graph, or at least one can establish it if works hard enough. And so now also I think the innovation of this method is to look not only at the maximum degree, but also at the codegree of vertices. And what is a codegree? So of a graph, it is a maximum possible number of common neighbors for two different vertices. And so here's an example, like in this graph, which I have constructed before. So here the degree of this graph is 3. So the biggest degree of a vertex is 3, and the biggest codegree is 1. And so here somehow the key element of the proof is that if our points are coming through, if you take like this random points in Euclidean space, then actually the resulted contact graph will have small codegree. So this is about the consequence of the geometry of Euclidean space. Because if we have two distinct spheres and compute what is the volume of their intersection, it will be small. So this is a key idea behind this. And so then the result, this logarithmic improvement, is essentially follows from this theorem for graphs. The theorem works for all graphs, also for those that do not come from this. They don't need to be contact graphs, so it's just a statement in graph theory. So let G be a graph on n vertices such that its degree is smaller or equal than delta, and its codegree is smaller or equal than this constant capital C times delta times log of delta to some power minus C, where capital C can be taken to be this particular constant and small c can be taken to be this particular constant. So then the theorem claims that the G necessarily contains an independent set of at least this size. And the independent set of this size is in fact sufficient to improve what we know about the sphere packing constant. And so as I told you, for somehow some people, like for example, there was an idea that okay, maybe this d log d, this is the correct answer, or almost the correct answer, but then the new bound comes, and so this new paper, it appeared only at the beginning of this month, and the theorem of Klartag, it actually works for again for lattices. So it seems like for many years, so lattice packings, they were ahead of all other packings. Then for a short moment, arbitrary packings, they got an advantage. But now the lattice packings are winning again in the race. So yeah, and so here the method is also like it's very interesting, and it is based on studying Brownian walk in the space of d-dimensional ellipses. And so here's somehow the heuristics behind the proof, somehow in a word, like in the, more or less in the words of the paper. So this is how things are supposed to work. So first we are fixing a lattice, and then we are starting with a nice, considering an ellipsoid centered at 0, and we would like to start with a nice ellipsoid which has has big volume, maybe the one which is guaranteed by Minkowski mean value theorem or by the Rogers theorem. And then we run a Brownian type stochastic motion in this space of ellipsoids. And the rules of the motion are the following. So our ellipsoid is evolving. It's somehow its volume is getting bigger or smaller. And the rule is the following. If ellipsoid at some point, if it meets a non-zero point of the lattice, then this lattice kind of becomes glued to the ellipsoid. And in the future evolution, the ellipsoid moves in such a way that it always preserves this point. And so somehow the space of ellipsoids, it has, if you are in dimension d, then the space of ellipsoids, it will have d, roughly speaking, d squared over 2 parameters. And so after the ellipsoid has picked this d squared points, it probably ran out of parameters to continue the evolution. And here somehow again, like a heuristic argument is that if we have this, if we imagine that this ellipsoid is somehow random and it has n squared points in it, then its volume also has to be something like n squared. But then of course this is only a heuristic argument, and there is a proof in a paper which I put here in a purple box, which probably should be a black box for me, at least at this point, but yeah, since I have black slides, I could not put it. Yeah, so there is a somehow proof which I still have to do my homework and understand, but then the proof tells us that with a positive probability there exists an ellipsoid such that it has no interior point, so this only interior lambda point is 0, and its volume is bigger or equal than some constant times n squared. And so, yeah, of course, maybe that's like last slide for today. So this is what we know so far for the sphere packing constant, and the question is, can we do better? So maybe next time there will be a paper which proves that like d cube, or
Any questions?
Thank you, Maryna. What do people believe is the right bound here? Is it like any power of d, or is it exponential improvement?
so I think people, yeah, so I don't think there is like a consensus in here. So my observation is that people who prove like lower bounds, they think that like the exponent is right and there is some polynomial improvement. People who prove upper bounds, they think that no, that like there should be an exponential. Maybe there is some kind of very unlikely set of points which have exponentially better. So I probably personally belong to this second group of people. So at least I don't know if it's reasonable hope or not, but I hope that there exist those like rare, strange, very good packings, and maybe we cannot see them because like they exist with probability 0 or with probability that tends to 0. That's why they are so hard to achieve by any kind of probabilistic argument. But yes, I think there is like, I know people from both camps and also anything in between.
Other questions?
Not a technical question, but why did you become interested in the sphere packing problem?
Yeah, so I don't know. I think it's it's an optimization problem where somehow we Yeah, but there is a hope to beat the greedy somehow. Like, so like in many optimization problems, like there are two methods we know. One of them is like random, another is greedy. And here there is a hope to beat those two. So maybe this is, yeah, this is what makes it so interesting to me. So it also seems like a fundamental question, like fundamental geometric question. So.
Other questions? Actually, maybe as I walk, on the previous slide, so that construction reminded me of these constructions from empty sphere. So if you'd like to find a configuration of points in d dimensions in which there are no obtuse angles, so the maximum number of such distinct points is 2 to the d, and the way to get such points is to look at empty spheres in lattices. So for example, the Leech lattice gives the maximum, so gives one such configuration in 24 dimension. And so so you also grow a sphere, there you grow spheres, but it's a bit similar than this random walk on that space.
Thanks for the talk. So I want to ask about the numerical difficulties you mentioned at the beginning of the talk for dimension 9. So can you comment on that?
Yeah, so maybe the comment I can give is that I spoke to people who work on the problem and they told me that it is hard. So yeah, so I never really tried to prove it myself, but yeah, also from the talks I heard that it is somehow, what I heard from experts is that they are trying to solve it and cannot do it.
Any more questions?
And what about dimension 3? Is the Hale's proof from the 90s, is it still the best proof, or is there hope for more conceptual ones?
So I'm not sure that actually, so here I have not heard from somebody tell me I'm trying on conceptualizing Hale's proof. So I don't know.
So people are considering this as an interesting question, so they kind of, it's considered done.
I have not met a person who would say me like this is something I would like to spend or a lot of my time on. So I guess if somebody has like an idea that would easily do it, then it's good. But yeah, I also think somehow it's it's probably maybe there is no much simpler proof. It's also a possibility that after all, this is an optimization problem where we know that there are uncountably many solutions, so it cannot be too simple. So the solution is not unique, right? So then this also probably for many simple methods, it means that most likely they will not work.
Final question?
So for those low dimension, do we believe the largest bound is the best, or the better bound?
Yes, I think for all dimensions in here, so I think it's kind of believed that this lattice is actually the lattice construction is the best. But yes, already but then for dimensions like this 4, 5, 6, 7, it's still an open problem, and probably maybe dimension 4 can be easier, but then probably 5 and 7 they might be not much easier than 3-dimensional case, because there is this uncountably many good solutions. Yeah, so maybe in dimension 6 I don't know, but maybe in dimension 6 there is some kind of simplification. So in dimension 4 there is a D4 lattice, and it's believed to be unique, and it also has some kind of nice. So it's I think it's a quite nice object. So we know there, for example, the kissing problem is solved in dimension 4, and now also a recent improvement is that now we know the uniqueness of the kissing configuration in dimension 4. This is a result, I think, from this year or end of the last year. And this also kind of gives hope that maybe after knowing this uniqueness of kissing configuration, maybe one could move forward and cook up some kind of argument for the sphere packing problem in dimension 4. But yeah, but then like 5 and 7 look difficult.
You want to ask another question?
Maryna, keep it further away. Maryna, so you mentioned that in dimension 24, the Leech lattice is the best lattice, and this you referred it to result of Kohn, and does it use the magic function, or it's
Probably, okay, maybe Henrik knows better, but yeah, so my understanding of that paper is that it uses the symmetries of Leech lattice, and then there is also, of course, some kind of numerical some optimization result in there, but maybe I don't know that paper so deeply. But
the paper was, in a sense, a publicity stunt. We had a 30-digit version of the magic function, and we couldn't prove that the actual magic function existed, so we were just trying to get as much as we could out of the approximate version.
That's what it was.
Any more questions? Yeah.
A bit stupid question. Are there any reasons why 8 and 24 are easier than, for instance, 12?
So I think here there is it's a good question, but I don't really know the answers. So there, just everything works well in there. So there, of course, the structure of the roots is good, and yeah. But then probably in dimension 12, I don't remember what is the best candidate, but maybe even there the structure of the roots, of the lenses, is good. But then here we do have this magic function, which also makes it, when in dimension 12, it turns out that the solution of the Kohn-Elk is linear programming. So it's numerically, it has somehow its zeros at the points which do not coincide with the lenses of given, lenses of vectors in the known lattices or known configurations. So I think it is some kind of a very, it's a coincidence, and it's even amazing how big this coincidence is, because we tried numerically to compute these magic functions in different dimensions. So when I say we, I mean Henry did and I did not. So we can numerically see where the roots are, and in other dimensions they just don't match. There is no good structure. They're not square roots of integers. They don't have any good structure. They're just somehow bad-looking irrational numbers.
Okay, let's thank Maryna again.